Delaware Tech, Chemistry 110, Unit 2 continued, heat of reactions, also known as enthalpy. Enthalpy is a general term for heat of any kind of chemical reaction. These are reactions that are either chemical in nature, where you're changing one chemical to another and you're looking at the heat change, or a physical change. You might be looking at changes from a solid to a liquid or a liquid to a gas, etc. And any kind of change in heat in a reaction is referred to as the change in enthalpy of that reaction. So the heat of fusion, otherwise known as the enthalpy of fusion, is abbreviated delta H. H is for heat or enthalpy specifically. So this delta H fusion is the amount of heat needed to melt 1 gram of a substance. Remember when we talked about conversion of one phase of matter to another phase of matter, or state of matter, we talked about solids changing to liquids. The colloquial word for that is melting, but the chemistry word for that is fusion. And it comes from an ancient Latin word, which literally means to melt. So fusion is another word for melting. Now, if you study nuclear chemistry, you'll find out that fusion has a totally different meaning, also in chemistry, meaning to fuse together or bring together two nuclei, two nucleuses of an atom to form one larger nucleus. But right now we're just talking about fusion as being defined as melting. So melting of any kind of substance. So the heat of fusion is the amount of joules necessary to melt 1 gram of a substance. And therefore, the heat required to melt a substance, which would be the Q is the total heat of fusion, would be whatever the mass of the material you're working with times the heat of fusion, or the enthalpy of fusion. Remember, mass is in grams, and the delta H of fusion is in joules per gram. So when you multiply joules times joules per gram, you'll just get joules, which is Q, our heat. So the heat of fusion, or the enthalpy of fusion of water, in other words, how much energy it takes to melt ice, is 333.55 joules per gram, or about 334 joules per gram. That's a lot of energy to melt 1 gram of ice to turn it into 1 gram of liquid water. The heat of vaporization, as the name suggests, is the enthalpy of vaporization, or the amount of joules to in this case, to vaporize or to evaporate 1 gram of a substance. So the heat required to boil a substance, or to vaporize or to evaporate a gram of substance, to evaporate a substance, the heat, the total heat, Q, is just going to be equal to the mass of whatever the substance you're dealing with times its enthalpy, or heat of vaporization. So remember, these delta H values are constants for each material. Every substance has its own heat of fusion, and every substance has its own heat of vaporization. They are constants. They are energy per amount of the substance. And in the case of water, the heat of vaporization of water is 2,257 joules per gram. So it takes an enormous amount of heat to boil 1 gram of water. And the reason why it takes so much heat to melt ice to water, and to even more to boil water, is you have to break all those hydrogen bonds that are holding water together. Hydrogen bonds are extremely important in water, and it requires a lot of energy to break those bonds up, to go from solid to liquid in the case of fusion, and to go from liquid to gas in the case of vaporization. So let's look at some examples of how you would use these constants. What's the energy required to melt 50.0 grams of ice? Well, we know the mass, and we know how much energy it takes to melt 1 gram, that's 334 joules. So we multiply 50 grams times 334 joules, and we get about 16,700 joules, and we usually write this in kilojoules because the amount is so large. So To melt 50 grams of ice requires 16.7 kilojoules of heat. That's a lot of energy. What about how much heat is released when we freeze water to its solid form, to ice? So remember, we still are using the heat of fusion, but now we're going backwards. So we just, in this case, the heat of freezing is just the opposite constant for the heat of melting or fusion. So instead of 334 joules per gram, we use negative 334 joules per gram, or we can just multiply and -1 times our answer in the end. We have 43 grams, we multiply that out, and we get 14.4 kilojoules released, or a total heat of minus 14.4 kilojoules. So remember to make sure you have the right sign. If you are gaining heat, in the case of melting ice, it's going to be a positive value. And if you're losing heat, as in the case of going from water to ice, because you're removing heat from the water to freeze it, that'll be a negative heat value. Boiling, now we're using the heat of vaporization, or the enthalpy of vaporization, the delta H of vaporization. We multiply 10 grams of water that we're going to boil times the heat of vaporization, and we end up getting 22,570 joules, or about 22.6 kilojoules of energy needed to boil 10 grams of water. And if we're going the other way around, we're talking about steam going back to liquid water. Well, now we're going to use the negative value for delta H of vaporization, and it's going to be 20 grams times the negative 2257 joules per gram to give us about minus 45.1 kilojoules. So you see there's a lot of energy involved in the phase changes for water, and that's because water is so hard to change from one phase to another due to the change in hydrogen bonding. Well, how do we measure these reactions, these heats? Well, we already learned about calorimetry. It's the study and the measurement of heat flow. And heat is measured with a calorimeter, and shown in this diagram is our classic coffee cup, our styrofoam cup calorimeter. This is the cheap version. There are much more sophisticated versions of calorimeters that are used in high-tech analytical chemistry labs. But you can envision this kind of calorimeter used, and you would if you wanted to measure the heat of the reaction, the total heat, Q, well, you can use a calorimeter. So you perform your reaction in one of these. Typically, you wouldn't do it in a container of water. You might do it in a container of water and do the reaction in water. But if the reaction is not in water, say you just want to melt something or freeze something, well, you want the calorimeter to be a high-tech version that has a jacket of water. So there's a layer of water between the two cups that make up the calorimeter, and that water can change temperature in response to the reaction that goes on inside the calorimeter. So what you have to know is no matter what kind of calorimeter you have, whatever reaction you're doing, whether it's a heat of fusion reaction, which is melting or freezing, a heat of vaporization reaction, which is boiling or condensing, or any kind of reaction, enthalpy, delta H of reaction, any kind of reaction, the idea is you're going to transfer the heat from your reaction to the water. And sometimes that increases the water's temperature if you're transferring heat from the reaction to the water, but some reactions absorb heat, and they'll remove the heat from the water, and you'll watch the water temperature go down. Now, we can't measure the heat of these reactions directly, but what we do know is that since heat is transferred, whatever the heat change in the water is that we can measure, it's just going to be the negative version of the heat transfer that happened from the reaction that we're actually interested in. So the Q of the water is just the negative Q of the reaction, and we can calculate the Q of the water directly from knowing the mass of the water, the specific heat of the water, and the change in temperature of the water. And we know the temperature changed because we have a thermometer in there, and we're looking at the before and after temperature. And then we plug those numbers in, and now we know the heat of the water, the Q of the water, and we might want to use the mass of the substance in our calculation later when we're getting the enthalpy of the water, the heat of the reaction, the heat of fusion. I know I'm using the word heat in two different ways. Sometimes heat means total heat, and sometimes heat means heat of reaction or heat of vaporization or heat of fusion. Those are heats per amount of a substance. And sometimes the heat is the amount per gram of a substance, so we might measure the delta H in joules per gram. And sometimes we might be interested in a heat of reaction where the units are kilojoules per mole. So we need to know the number of moles of our substance. So no matter which way we're going to do it, we're going to need to calculate how much heat was transferred to water to get our heat of reaction. And we can use either joules or kilojoules. And then we need to know how much substance was in that reaction. Was it either in mass units, which are grams, or in moles? And you can create these two different versions. There are actually many different units used for delta H, for enthalpy. These are the two most common. So let's look at some problems that do this, and we'll look at problems that focus on the kilojoules per mole version of these reactions. And these two reactions are both reactions where you're dissolving some substance, in this case two different salts, in water. And that will change the temperature of the water, because these reactions either produce heat, in the first case, or they absorb heat, in the second case. Remember, a reaction that produces heat is called exothermic reaction. So calcium chloride in water will release heat, and you can see in this case 7.8 grams of calcium chloride is added to 80.00 grams of water at 22.3 degrees Celsius, and the temperature increases to 45.1 degrees Celsius. Whereas in the second case, we have 32.1 grams of ammonium chloride added to 125 grams of water at 28.9 degrees, and you see now the temperature drops to 19.4 degrees centigrade or Celsius. So the first reaction is releasing heat to the water, that's exothermic, and the second reaction is absorbing heat from the water, that's an endothermic reaction. But that will only change the sign. It won't change how we calculate the actual values. So let's look at the first value. We know the number of grams of calcium chloride, we know the number of grams of water, we know the before temperature, we know the after temperature, and we're going to assume the specific heat for this reaction is the same specific heat as plain water. And this is a reasonably good approximation. So we plug this in. We have the heat, in this case, you'll notice all the other cases before, we would use the mass of just the water. But these are dissolving reactions, so they're mixed together. The water is part of the reaction, and therefore you have to add the two heats together. So our total grams of material is actually 87.80 grams of material. And they are both changing in temperature from 22.3 to 45.1 degrees centigrade. And if you plug this into our famous Q equals MC delta T equation, we get that this reaction is releasing heat to the water in the amount of 8,375.699 joules of heat. So this is the heat that the water has absorbed from the dissolving of the calcium chloride in the water. Now that we know the heat that the water gained, we automatically know that the heat of this reaction, in this case the solvation of calcium chloride, is the negative version of that, and we change it to kilojoules, so it's negative, it would be negative 8,375.699 joules, and we turn that to kilojoules, negative 8.3757 kilojoules. Now you notice I haven't rounded any numbers. We don't do the rounding to the very end. So we now know the amount of energy, and then we're just going to divide it by in this case, moles of the calcium chloride. We're not going to worry about the water, we're just worried about the calcium chloride. So the calcium chloride, to get the moles of calcium chloride, first we need to know the molar mass. So we add up the molar mass of the calcium plus 2 molar masses of chlorine atoms, and we get 110.984 grams per mole. We know how many grams, 7.8. We multiply the we take the number of grams and divide it by the molar mass, and we get the number of moles. So you'll notice now, at this point, we know our energy that was used. Let me get the highlighter here. We know how much energy was produced by the reaction, and we know how many moles created this reaction. And we're literally just dividing the first number by the second, and we end up with minus 119.175 kilojoules per mole. And you'll notice, since this number only has 2 significant digits, that means that our number of moles really had only 2 significant digits, and therefore our final answer should only have 2 significant digits. So our answer is minus 120 kilojoules per mole. In other words, this is telling us how many kilojoules how many kilojoules of heat are released into the water every time you dissolve a mole of calcium chloride. 120 kilojoules per 1 mole of calcium chloride. And since we're releasing it, it's negative. Let's look at the second example. We've got 32.1 grams of ammonium chloride, and we're adding it to 125 grams of water. This is a reaction where the two are mixed, so we need the total grams. We know the before temperature, we know the after temperature, which in this case is lower, and therefore when we calculate our change in heat of the water, which is Q of the water, we will have a negative value, in this case negative 6,244.4108 joules of heat that the water actually lost. The water transferred its heat to the dissolving of the ammonium chloride. This is an endothermic reaction. And because of that, the heat of the water is, remember, the heat of the water is always going to be the negative of the heat of the reaction. We take the negative value and we convert it to kilojoules, and we get that the heat of the reaction in this case is positive 6.2444 kilojoules of energy. In other words, this is a positive energy change because the temperature has gone down in this case. We also need to know the moles of ammonium chloride, and we get that by adding up the first we have to determine the molar mass of ammonium chloride. We get that by adding up the molar mass of the nitrogen, 4 hydrogens, and 1 chlorine atom, and we get that the molar mass of the ammonium chloride is 53.491 grams per mole. We use that to convert our 32.1 grams of ammonium chloride. Remember, we only are interested in the grams and moles of ammonium chloride in the end. The heat is something different. That's why we include it, because everything was changing temperature. But when we want to know how many moles were responsible for this reaction, we only look at the moles of ammonium chloride, and that's 0.6001 moles of ammonium chloride. So again, we now have our heat of the reaction, and we have our heat that was transferred in the reaction, and we have our number of moles that were involved that we divide one by the other, and we get the heat of the reaction, more technically called the enthalpy of the reaction. In this case, the enthalpy of solvation of the ammonium chloride is equal to plus 10.4 kilojoules. And you'll notice we finally round it. We round it to 3 significant digits. If you look at the original problem, all of the numbers have 3 significant digits, and we end up with a value of plus 10.4 kilojoules per mole, which tells us that every mole of ammonium chloride will result in a change of 10.4 kilojoules of energy. In this case, it is removing that energy from the water. And with this, we will stop here.